This meeting is being recorded.
Okay, excellent. So in space, no one can hear you hack. So computers are everywhere in space. And this image in the center here is what it looks like in the International Space Station. So as you can see, there are computers in space, and there are a lot of them, and they're running all types of operating systems, including the types of operating systems we have on the ground. So you have Linux and Windows, and as we'll find out, a lot of obscure operating systems with a lot of source code based in the 1990s that haven't been updated in decades. I mean, it's fantastic. There's as much as there's a lot of equipment to hack on the ground, there's even more stuff to hack when you include everything in space, everything around Earth, everything in deep space. So there's even the Voyager spacecraft, which are outside our solar system. So we can even hack stuff in interstellar space, kind of. I mean, if you could get access to the Voyager uplink and downlink. So who am I? This is a bit outdated. My name is Caitlin Handelman. I was at NTT Data as of 2 weeks ago. I have since moved to Amazon, and I was a security engineer. Now I am an offensive security engineer. And at the time, there was a little secret. I wasn't allowed to tell people publicly due to concerns over APT groups and other hostile nation states, but I was at NASA. And now I'm actually over at Amazon working on the Kuiper space mission. So securing essentially what Kuiper is, it's a competitor to Starlink. So I'll be working on that space program for a while. So why am I doing this? Well, I'm always learning as well. Learning about space and space hacking and all the technologies involved has been a very challenging and much harder experience than I was expecting. I thought going in, well, these are just computers in space, and I can hack computers on the ground. How hard could this be? It turns out it's actually kind of hard, and there's a lot of stuff I had to learn, and I'm still learning. And I always say, you remember about 10% of what you're taught and about 90% of what you teach. So this is as much about me teaching you as me, reinforcing and teaching myself. So we're going to be talking about how we get into space, about basic cybersecurity in space, hacking weather satellites, which is how I think it's a great place to start if you're interested. And we'll talk a bit about the Deep Space Network, which is, oh boy, that is awesome. We talk about the internet here on the Earth. There is a quote unquote internet in space called the Deep Space Network. And it is just another network that anyone can go on to and see the traffic going through it. It's amazing. Anyway, we'll talk a little bit about FPGAs, which are field programmable gate arrays. This is hardware that you can reprogram, and these are used a lot in spacecraft because a lot of times you have one-off systems being built. And if you, instead of fabbing an entire silicon wafer, for a single product that's going to be made, a lot of agencies and a lot of spacecraft will use FPGAs, so it's important to know how they operate. We'll talk about the operating systems used in space, a little bit about open source software. And this was a special request from Sam a long time ago, but generating nuclear power at home. So let's talk about getting into space. What does it take to actually get a payload into space? So there's this famous rocket equation. And basically, if you boil this down, there's something called delta V. This is delta. The triangle here is delta. The V is V, and that means the change in velocity is a function of how good your engines are. This is called the specific impulse, and your initial mass, and your final mass. So basically what happens is you have a certain amount of speed that you can change on a rocket. And the faster, and how do I put this? It is based on how much fuel your rocket has at the beginning and how much fuel it has at the end. And you can hack this equation in a way that we can get a lot more speed out of our rockets by using something called staging. So you'll have one big rocket at the bottom, and then a smaller rocket on top, and then even a smaller rocket on top of that one. And you can use that to sort of bend this equation so that you can get really fast and start sending large objects into orbit, to the moon, to the distant parts of the solar system. And it's really just a simple equation. And that's most of the time when you're getting into space and you're working on rockets, this is the most important equation you need to know. Right. So yeah, so the important rocketry terms that you're going to hear a lot in space is delta V. As I said, that's the change in velocity. So you have a delta V budget. So like, let's say you can change 2,000 meters per second total. That's your delta V budget. And you can use that to offset rotation. You can use that to change your orbits, to speed up, to slow down, essentially. But once you use up that budget, you're done. Your fuel is spent. There's something called specific impulse, which has to do with engine efficiency. So if you have a good specific impulse, you can use your fuel very well. So you can think of something with a good specific impulse as being something like an ion drive, which is essentially uses charged gases to very gently push a spacecraft, into higher or lower orbits over the course of half a year. It's a very slow process, but it's very efficient. So sometimes you don't necessarily want the most efficient engine because that engine, of course, won't let you get off the ground. And that brings us to the thrust to weight ratio. So that's how much thrust you generate compared to how much weight the rocket has. So to get off the ground, you really need a good thrust to weight ratio. And sometimes that means just using really powerful, really inefficient rockets. Then when you're in space, you might switch to something that has a higher specific impulse. And of course, staging, like I said, is the hack to the rocket equation, where we just put a rocket on top of another rocket on top of another rocket to get into space. And of course, when you get into space, our main goal is to get into an orbit. So there are two parts of an orbit. There's the Apoapsis and the Periapsis. And maybe you've heard the term like perigee or apogee. Same thing. So, go on. Oh, I thought I heard something. So a apoapsis is the furthest part of the orbit from the main body, and a periapsis is the closest part of the orbit to the main body. So when you hear apsis at the end, peri, that means close. Apo means far. So you have perigee, apogee, and in relation to Earth. So if you hear that as well, that's what they're talking about. And of course, we're not always orbiting just around the equator. Sometimes we're orbiting at a little bit of an incline. So the point where where the spacecraft will essentially go past the center equator is either called the ascending node or the descending node, depending if it's going above or below, and the angle of inclination. So for example, a lot of weather satellites have a very high angle of inclination. So they'll do polar orbits. Because if you think about it, if a weather satellite was only orbiting the equator, they'd only get images of the, a band of the equator. But if you put a weather satellite in with a very high angle of inclination, it'll go around the North Pole and the South Pole, and the Earth, of course, is rotating 24 hours a day below, and you can use that to get a very wide coverage. This is actually going to be pretty hard to do. Let me switch to, let me find Zoom. I can't find my Zoom window. This is not good. Oh, here we go. I'm going to share my screen. Actually, I'm not going to share my screen yet. Let me pull up the video first. I have way too much stuff open right now. So I want to show how this works. Here we go. So there is a game if you want to learn about how rockets work. It's called Kerbal Space Program. And I recorded a video showing a typical rocket launch and how that actually looks, at least virtually, in this game, Kerbal Space Program. So let me share my screen. Here we go, movies and TV. So this is this is what it looks like in the game. And there's a payload inside a fairing, essentially, so that the thing at the top will split open once it's in space, but we need to protect it from the wind. And that window I'm dragging around at the top is actually I'm looking at my Delta V budgets. Like I said, that is a very important part of any sort of space rocket engineering. So you start off at a launch pad, and generally rockets are going to start going straight up. And then after a bit, start turning towards the east. And the reason why you want to turn towards the east is because we want to work with Earth's rotation to get us into, orbit faster. So most rocket launches, you'll see they'll go up and to the east. So let me speed ahead here. So you'll see that the rocket goes to the east. Yeah, so it's now heading towards the east. And we'll keep going up, and we're circulating our orbit a little bit. And so our goal is not to go up. If you were to go straight up, you would just fall right back down unless you achieve, escape velocity. But even that would be a very inefficient way to achieve escape velocity. And what we saw right there was a staging. So notice we had this big rocket ran out of fuel. It now drops off, and now we have a smaller rocket. And this is the map view. And you can see the orbit beginning to be created. So this is a suborbital trajectory I'm currently in, because we're still trying to get into orbit. And so this small rocket is going to keep going up. And then once it reaches its apoapsis, it's going to turn horizontal to the planet and start burning. And that's how we're going to circulate the orbit. So we're going to speed ahead here. And yeah, here we go. The next burn, we're circulating the orbit by just burning prograde. So we're burning with the direction that we're already heading in space. And it takes a long time, so I'm going to speed up again. Speed up, speed up, speed up, speed up, speed up, speed up. Oh, and we can see that blue circle right there is our projected orbit, our current orbit. So you can see it getting larger and larger and larger. And we just staged again. So now we have an even smaller rocket, and we're circulating the orbit, and there we go. That's how you get into orbit. So you go up to the right, you get into a suborbital trajectory, and then you burn prograde to essentially achieve the orbit that you want. And you can try this yourself using a program called, like I said, Kerbal Space Program. Let me switch back in Zoom. Stop share. There we go. All right, on to computers. Cybersecurity in space. And yes, satellites have computers, and they can totally be hacked. Now, of course, satellites are not necessarily going to be on the internet. Now, I have seen examples of people, quote unquote, hacking satellites by essentially hacking into the command stations, getting the passwords, going in, and then working with the command station on the ground to essentially hack the satellite. But what's really going on is that you have ground stations, and I mean, we've all seen this, right? You when the NASA launches or you go to the ground control, you have these giant rooms of people sitting behind consoles, looking at flight dynamics and communications. And essentially what happens is you have, your basic network structures you see everywhere else, where you have some TCP data, TCP IP data, going from the flight control computers to a cryptographic unit to something called an SDR, a software-defined radio, which essentially encodes it into radio waves that are going to be transmitted. That gets sent to an antenna. And then, of course, those radio waves radiate off into space to the antenna on the spacecraft. And then the opposite happens on the spacecraft. So the data from the antenna, the raw radio waves, go through the software-defined radio, gets decrypted, and then turns back and usually right back into TCP/IP data, back on the spacecraft. So you're although there are weird buses and stuff like Space Bus and a few other things on spacecraft software buses, a lot of times you will see the same technologies in space as you do on the ground. So, for example, TCP/IP data, will be on the spacecraft as well, and the reverse is true too. So it'll just go through the reverse process of going from the space vehicle back to the ground station. And the space vehicle bus usually are segmented into two different portions. So you have the flight portion and the payload portion. So as we saw on the spacecraft, there's usually an antenna, a software-defined radio, and that goes to the data handler. So it gets the data, and the data handler needs to figure out where it's going to go. So if the data needs to go to the flight computer will then handle things like the torque rods. So a torque rod is a way of using Earth's magnetic field to spin the spacecraft without using fuel. Very neat. Oh, yes.
Can you move your face up to the top? You're covering part of the slide.
I absolutely can. In fact, what I can do is I can do something better. There we go.
Great,
Thank you. Thank you for letting me know. All right. So we have torque rods, flywheels, RCS thrusters. So RCS are just like small rockets you can use to make small movements. And of course, the thrusters themselves, so the big rockets. Or the data can get sent to the payload computer, which would then get sent to things like, the sensors, the imagers, the things taking readings on the spacecraft. And we'll get into more of that later. The most space hacking, I would say, happens over here in the payload computer. That's where kind of you can load custom software and stuff very easily. And it is very easy to load custom software onto a lot of these systems. They are designed to be updated. So when you're talking about spacecraft, there are a few different domains. The most common is low Earth orbit, and things like Starlink, which orbit very close to the Earth, just 100 kilometers, maybe a little more, maybe a little less. There's medium Earth orbit, which is sort of a little bit more out there, and there's not a whole lot in medium Earth orbit, but the most famous is GPS satellites, which sort of hang out and lazily cross the sky every once in a while. And then you have geostationary orbits, and this place is packed. So geostationary orbit is an orbit that takes 24 hours to orbit the Earth. So essentially, it looks like, from our perspective on the ground, that the spacecrafts are just sitting in space in the same place day in and day out. And so this is where you have a lot of your TV channels, where you have those like little dishes. You've seen, like the TV dish that that people put outside their windows, and they're just pointed in one place in the sky, like DirecTV. And that's because the satellite doesn't appear to move from our eyes, because it takes 24 hours for that satellite to fully orbit. And that is a very specific orbit. It's very crowded. And then, of course, you have deep space. So these are anything further than geostationary orbit. So anything to the moon, to Mars, to Jupiter, outside the solar system, interstellar space, that's all considered deep space. So what could possibly go wrong with putting equipment in space? Well, a lot can go wrong. And this is the first thing you have to know about cybersecurity in space, is that so much can go wrong. You have radiation everywhere. So in low Earth orbit, your spacecraft is bombarded by protons, which can literally crack the crystal lattice in silicon. And then, of course, in higher orbits, the Van Allen radiation belts bombard your spacecraft with electrons, which induce tons of voltages. Lots of fun. You have temperature swings. So when you're in space, there's nothing to really shield you from the sun. So you can go from like hundreds of degrees Celsius to like negative several hundred degrees Celsius, all within a couple hours. Fun times. You have collisions with asteroids and like the little meteorites and stuff that can hit your spacecraft just out of the blue. You have collision with other satellites, which brings us to a really fun topic, Kessler syndrome, where a satellite will break up, and that will break up into smaller pieces and hit other spacecraft, which will break up into smaller pieces, which will hit more spacecraft, which will break up into smaller pieces. And eventually no one can get into space because everything has been broken up into these small bullets that are essentially flying in Earth orbit. And by the way, it's happening right now, Kessler syndrome. It's a very slow process to get to the point where we can't get into space, but there have been studies done, and it is looking like the beginnings of an exponential curve of space debris caused by collisions is happening. So this is something we really need to think about moving forwards. So there's lack of testing. So you can, testing your spacecraft can be expensive. So maybe you put it up there and realize, oh, we made a big mistake because we didn't test enough and your spacecraft goes down. Launch vibrations is a big thing you have to consider when you're designing your spacecraft. When rockets are very noisy, they're very loud. There's a bunch of equations you can use to figure out just how loud, and it's loud. And you have to figure that in when you're designing your spacecraft. And of course, your rocket could explode on the spacecraft. Your rocket could explode on the launch pad. And then let's continue. The space vehicle could fail to deploy. Like you have solar panels, they don't go out. You could have uncontrolled tumble, which is where your spacecraft sort of spins around in space. It can't figure out what to do. You have power failures where you're just not getting enough power. The batteries fail. The solar panels are not going right. Your own emissions, for example, when you start getting into radio, you realize that every electronic device is both a radio and a receiver. So your own emissions from your spacecraft can interfere with your communication with the ground station. You could deorbit by accident. And the anomaly. Yeah, the anomaly can totally destroy your spacecraft. What's the anomaly? The South Atlantic anomaly. So the Van Allen belts, it turns out, gets very close to Earth's upper atmosphere in this specific region called the South Atlantic anomaly. And there's a map here of memory upsets. So this is where a charged particle has hit a spacecraft and caused a bit to flip. And you can see it's all clustered around this one area. And if you have a spacecraft, it's likely going to eventually pass through this region. And you're just going to have lots of strange hardware stuff happening. So unlike cybersecurity on the ground, where cybersecurity is like the most important thing, right? Sure, there's fires and floods, but what you're mainly worried about taking down your systems are hackers. In space, cybersecurity is threat number 72, right? It's not taken as critical as these other threats, which are much more dire. They have to deal with. Furthermore, you can't have things like traditional anti-malware software and anti-virus solutions running on your systems because you're dealing with very restricted setups where you have very limited resources and very limited power. So you can't just run whatever you want. You have to be very selective, and usually that means not running any cybersecurity software. And so robustness and isolation are really key in just designing your spacecraft. So just assume it'll get hacked and then work from there, as opposed to assume your spacecraft is totally, not able to be hacked and then find out it can be. And many spacecrafts will disable encryption if it cannot communicate with the ground, because so many things can go wrong. You need to recover your spacecraft. And so this is just a known vulnerability in all space vehicles. So what can a threat actor do? Well, once you get control of a spacecraft and you can get RCE, one attack that has been apparently been used by hackers is to tell the payloads to use all the power at boot up. So you send a new boot executable, telling it to turn on all the radios, all the imaging sensors, everything at once. The second it boots up, it does that. It runs out of power again, shuts down, waits to build enough power, boots back up, same thing, just cycles and cycles, and you DOS the satellite. You can compromise the SDR, the software-defined radios, change frequencies, change the encryption, do that kind of fun stuff. You can interfere with navigation. So the way that a lot of spacecrafts will navigate in space is either through something called a star/sun tracker. So it'll just look where the stars are or where the sun is to figure out its location. Or more commonly, especially in low Earth orbits, spacecraft will use GPS, and GPS is incredibly easy to manipulate. You can do that actually at home with something called a HackRF. You can manipulate the GPS signals. They're very weak, even in low Earth orbit, and you can completely make your satellites think they're somewhere they're not. You can use thrust to mess up the orbit or cause your spacecraft to deorbit. You can permanently disable communications. I mean, there's no reason you can't. And from the ground, of course, you can just jam communications. You can send so much junk radio waves towards the satellites that it completely jams it up, and the operators can't do anything with the satellite anymore. And of course, you always have to deal with people on the ground stealing or interfering with the design itself, a sort of a supply chain attack, which can happen absolutely in space. And of course, you can, I mentioned supply chain. You can poison the test data. So you can make it seem like the spacecraft is operating successfully when it's not on the ground. And then when it takes off, the operators are in for rude surprise. You can take over the ground station, like I said earlier. I've seen this done before. Why go after the satellite itself? You can just take over the ground station. And of course, the ground station might have third-party consumers of data that you can take over. A lot of payloads will send data to very specific people of interest. So an imaging sensor might be taking images of a specific like rainforest and send that off to the rainforest scientists, and you can get in there and steal their payloads or their data, I should say. And of course, like I said, you can install malware on the bootloader or on top of the flight systems and have all kinds of fun spoofing data onto the bus, etc. And so what can you do to defend spacecraft? Well, you can have watchdogs, scripts and programs. So anytime the spacecraft is doing something it's not supposed to do, you can have something on there raising red flags. You can't necessarily have a full antivirus suite or anything like that. But for example, if power is being drained too fast at boot up, like I said, you could have a watchdog say, hey, no, we got to shut everything down until we get back up. You can have gold copies of the software and the data on board. So that if something goes wrong, you can do a fallback as soon as possible. So if there's like malware that gets uploaded, you can fall back to a previous state that does not have the malware, and you can regain control. Fallback encryption, like I said, instead of having one encryption scheme and then falling back into plain text, you could have an encryption scheme. And if that encryption scheme fails, try encryption scheme 2 and 3, and then finally, if all those failed, then as a last resort, go to plain text. Like I said, you could have, and this goes along with watchdogs, resource limits. So if you're using too many resources, shut things down automatically. And of course, you can isolate the buses and resources. One of the things I've noticed in working with a lot of space vehicles is that the space buses, the bus on which data and applications are shared, tend to have a very 90s trusting model, and everything just talks to each other willy-nilly. And one of the things that space craft designers can do moving forward is to actually isolate these buses. So if one aspect of the space vehicle does need to be talking to another aspect, you can isolate them and prevent damage from an attacker. So yeah, let's go on. Let's see, how do we hack satellites? And as you can see here in the center, this is something called a software-defined radio. You can get these at home. These cost about anywhere between $200 to $800. Sorry, $20 to $800. So this one in the screen is probably about $20, and it's fine to get these started hacking satellites. You don't have to spend a whole lot of money to get started. So before we start talking about working with SDRs, I want to talk a little bit about the way that light is polarized. And so I'm sure we've all seen polarized sunglasses where the light is polarized either vertically or horizontally. So that, and the reason why we polarize sunglasses is to get rid of a lot of the glare off the ground. So I believe they're polarized horizontally. And a radio wave is going to have that same polarization, horizontal or vertical. And so if you look at, for example, a TV antenna, that is using horizontal polarization. And so if you look at the roofs of people with large TV antennas, you'll always see I'm going to call them the arms. This is a Yagi antenna. The arms of the Yagi antenna are horizontal with respect to the ground. And that's because TV stations send out horizontal radio waves. And by the way, if you have a pair of rabbit ears on top of your TV, I don't know who does anymore. Likewise, if you want the best reception, a good idea is to make them horizontal. There's also something called circular polarization, which we don't use a lot on the ground, but it makes a lot of sense in space vehicles. And this is where instead of having a strictly vertical or strictly horizontal polarization, the radio waves sort of make the electromagnetic waves, I should say, make a sort of curly Q, either clockwise or counterclockwise spin, outwards and inwards from the antennas. And this is really useful for spacecraft because, of course, vertical and horizontal polarization is always in respect to the ground. And in space, up and down make no sense. So when you're talking about sending radio waves in space, you want to use circular polarization of some kind to make it easier to receive. And so this is an example of a circular polarized antenna that I just threw together from parts I got from the local hardware store. This is a quadrifilar helicoidal antenna. That's the proper name. And it totally works to get satellite data from low Earth orbiting satellites. And so to begin, the satellites I recommend people look at first are called NOAA 15, although NOAA 15 is kind of falling apart. NOAA 18 and NOAA 19. And they operate between 137 and 137.1 and 137.9. And so that's just above the FM frequencies, like your FM radio. And what these are, what NOAA 15, 18, 19 are, they are weather satellites. And so as they pass overhead, they're going to send over the data of the images that they're collecting on something called APT protocol, which is the automatic picture transmission. And you can just receive it with, like I said, an antenna like this that you can make at home or something similar. I've even seen people use dipoles, which is just two long wires connected to each other to collect these signals. And if you do want to make your own quadrifilar helicoidal antenna, which receives the NOAA satellites very well, there is a calculator that you can use online to just figure out how long you need to make each leg. And you can just follow that, follow the instructions. And like I said, there's also instructions about how to wire it up. Let's move forward. All right, so in order to transmit a signal, you have to modulate the wave that's coming out so it contains data. So the first way or I should say not we, but early engineers 100 years ago decided to modulate a signal is to use something called AM, or amplitude modulation. And that's where you essentially modulate the strength of the wave coming out. So you have a set frequency, like 500 kilohertz, right? And then you modulate it up and down to create a smaller wave, essentially a lower frequency wave that people can hear. And that's where AM radio comes in. And you can use that to encode any sort of sound, or any sort of data, not just sound. And then you also have frequency modulation. And what frequency modulation does is it moves the frequency left and right, or upper and lower, I should say, to create another sort of waveform or to encode information. And what we see here is an example from an SDR output. So to the left is lower frequencies, and to the right is higher frequencies, and down below is the history. And so as you can see, as the FM radio station, 95.7 FM, it transmits lower and higher, and below that, you can kind of see that there's a sound wave that's being produced, like something you would see in Audacity if you ever use that program. And that's where FM modulation comes in. And in computing, we're actually not using either of those most of the time. We're using something called phase modulation, precisely because we are using SCR so much. And that's where you just change the phase of the wave coming out. So a phase is what part of the wave is being transmitted. So you have like the start of the wave here where it goes above the 0 point. And then you have another phase below the 0 point, and then you can switch the phase so it's below the 0 point again, so on and so forth. So you can use that to encode data. And that's used a lot with software-defined radio for reasons we'll get into maybe a little bit later. So in order to grab some data from like one of these orbiting NOAA satellites, what you do is you set up your SDR and your SDR software, and you're going to set up your antenna and start listening on FM. And each NOAA satellite has its own frequency it broadcasts at, and you're going to start hearing a signal come out. And it's going to sound like beep, 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 beep. And actually those beeps that you hear, or it actually sounds like a clock, like a metronome, like clock, 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 is a line of an image coming through. And so basically what it's doing is it's encoding a sound using FM radio, and that sound encodes an image of something passing overhead.
Caitlin, apparently
Yes.
they've got to go fill out forms at 9:15. I thought it was
9:15.
9:30. So we better
Okay.
stop here and resume when they come back, which I guess is 15 or 30 minutes.
Okay, perfect. So I can get set up with a demonstration of how to decode APTs while they do that.
Okay, I'll stop this recording and make another one later.
Okay.